Natural hazards and increased traffic demand pose as threats to performance of transportation networks. The EU Horizon SAFE-10-T project aims at mitigating sudden infrastructure failures by maintaining of minimum safety levels across the 10T network through proactive maintenance planning. Within the project, the normal methodologies are developed for reliability analysis, multimodal traffic analysis, and whole lifetime assessment, which are pertinent to critical infrastructure such as bridges, tunnels, and earthworks. These methodologies are aligned to form a consistent risk-based framework that is practically implemented as a decision support tool, in short called the DST. The data required for the DST, as well as its outcomes, are stored in a customized big data platform. The DST framework allows quantitative analysis of what-if scenarios, which include threats, related asset failures, and consequences thereof to stakeholders of transportation networks. Herewith, the DST supports the decision-making process on planning optimal maintenance to mitigate the risks of failure. The SAFE-10-T DST is developed as a web-based prototype application. It provides fusion and visualization of the relevant data on a critical asset and the related traffic network, which are to be used in the risk analysis. More importantly, the DST enables quantitative risk evaluation and provides risk visualization to indicate the optimal maintenance strategy for mitigation of risk related to inadequate asset performance. The DST is accessed via web, and its main window comprises a GIS map of an infrastructure network with a selected critical asset. The overview of the essential data for a quantitative risk evaluation is available in the threat scenarios and maintenance data menus. The latest version of all input data is obtained from the Big Data platform with a click on the Update button. The threat scenario menu gives summary of the crucial data on the predefined threats and dominant failure modes of the critical asset. Here, the default information on the direct costs of failure, duration, and type of related traffic disturbance can be modified by user. The failure of a critical asset causes change in traffic flow, which in turn lead to longer travels. The related additional travel time in hours and additional pollution in kilograms of specific pollutant are supplied to the DST. Using pertinent unit costs, these consequences are monetized and presented here as annual indirect consequences for a traffic scenario, year, traffic mode, and the environmental impact. In this particular case, a fatigue failure of a bridge is investigated for traffic growth, thus a threat scenario is regarded equal to the traffic scenario. Further in this menu, the tabular overview of default values for 4 risk parameters is given. Threat scenario occurrence rate, failure mode occurrence rate, direct and indirect costs are given per specific year and relate to the case where none of the predefined maintenance scenarios are applied. The maintenance data menu gives summary on the predefined maintenance activities and their effects on traffic disturbance, as well as the related implications on the annual budget. The default data on maintenance activities comprise information on the schedule of their application, direct costs, and the related traffic constraint, which all can be specified by user. For each maintenance activity and chosen traffic scenario, monetized annual indirect costs can be overviewed per traffic mode and environmental impact. The maintenance activities may be planned on working days or weekends, and the related impact of this choice on the consequences of the traffic disturbance can be readily seen. The presentation of annual indirect costs is similar to the case of threat scenario, and the cost setup is shared between threat and maintenance windows. Therefore, the modification of related unit cost data affects evaluation of indirect costs in general. The annual sum of direct and indirect costs of each maintenance activity can be reviewed in this menu as well. The traffic disruption due to an asset failure or a planned maintenance activity can be visualized on the GIS map. This feature works for the data selected in the threat scenario or maintenance data window. There is a possibility to visualize 2 effects of traffic disruption, and these are congestion level and the change of travel time. The traffic congestion for a specific time of the day can be reviewed separately for each direction of traffic. Here, a color spectrum from green to red is used to present the ratio of traffic load to the capacity of a traffic link. The change in travel time on road links is represented by using different link widths. The thicker the link is, the larger is increase in travel time by passenger and freight traffic on this link. The Risk Analysis menu is opened with a click on the critical infrastructure asset. Here, the impacts of various maintenance strategies on the temporal risk can be reviewed for each threat scenario. The central feature here is the temporal risk graph, where the upper part of the y-axis displays the evolution of annual risk over time. In accordance, the information on the direct, indirect, and the total cost incurred by maintenance activities are presented in the lower part of the y-axis. The reduction in risk is understood as a benefit, and it is evaluated as the net present value. The maintenance scenario with the highest net present value can be regarded as the optimum one. The annual maintenance budget can be specified in a sidebar. This is displayed in the graph to facilitate the comparison with the direct costs of the maintenance activities. There are two additional features that enable better insight into risk mitigation, and these are parallel coordinate diagram and the risk graph. In these, the same color code for predefined maintenance scenarios is applied. The parallel coordinates diagram feature enables seamless graphical filtering of all relations between the input and calculated data which are not readily observed in threat, maintenance, and risk analysis windows. The axes in this diagram denote year, maintenance scenarios, maintenance activities, threat scenarios, and all risk parameters. The data filtering is interactive and performed by selecting a range or several ranges of values on desired axis. With this type of data visualization, all crucial information on risk analysis is at user's fingertips. The user can grasp the value and importance of data and, most importantly, understand where the highest risks are coming from. For example, the diagram gives the possibility to trace what threat or a failure mode generates the highest indirect costs, or observe what are the effects of certain maintenance activities on risk drivers in a certain period. The Rescale Graph feature clarifies both short-term and the long-term impacts of specific maintenance activities on the two risk parameters. The first parameter is the annual failure rate, which is given in the logarithmic y-axis of the graph. It represents a product of the threat and failure mode occurrence rates. The second risk parameter is the total cost of failure, given on the x-axis. It represents the sum of indirect and direct costs of failure. The risk scale in this graph is represented with the predefined color spectrum ranging from green to red, denoting the change from low to high risk values. For the years with maintenance activities, the related risk values are presented as a pair of dots, one just prior to the activity and the other one just after the activity is performed. The straight lines connect the subsequent annual risk values, and arrows denote the direction of change in risk over time. The targeted users of the DST are the owners or operators of transportation networks that strive to make robust yet cost-effective decisions on maintenance of critical infrastructure. Here, the DST application provides fusion and visualization of the data on risk parameters for a critical asset and related traffic network. By using the novel features for risk visualization, infrastructure managers get a clear insight on the benefit that comes from reduction of annual risk by timely application of maintenance activities. The essential aspect of the DST is its high versatility to meet the future client needs in both software and methodological sense.